Professor, I will inform you after 40 minutes that we have only 5 minutes left. Okay.
Mhm. Sounds good.
Okay. So our next speaker in today's Majorana-Raychaudhuri seminar series is Professor Raymond Ko from Indiana University, US. And thank you, Professor, for joining us so early in the morning. And his title is Solving Cosmological Mysteries with Axion Rotations. And Professor, the screen is yours.
Thank you. Yeah. Today I would like to discuss how we can use what we call the axion rotation as the specific axion dynamics in the early universe to solve cosmological mysteries. So before I begin the talk, I just want to take a moment to commemorate a few physicists who won the Nobel Prize in physics and in chemistry exactly today, in various years. So today is actually a very special day. A lot of people were born today or passed away today. And those are the people who won the Nobel Prize in physics and chemistry. All right, so all I have to talk today is to go beyond the standard model. As we all know that the standard model is very well constructed to explain almost everything in the universe, except a few small things and a few big things. One small thing is that in the neutron, we have the constituent quarks, and we expect it to have some electric dipole moment, but somehow the experiment tells us that the electric dipole moment of the neutron is vanishing, and that's called the Strong-Levy problem. And also in dark matter sector. So what we know in the universe is that we have the rotation curve of the galaxies, but the stars are rotating much faster than we expect from luminous matter. And one explanation for it is the dark matter that is providing the extra gravity to have the rotational curve what we observe today. But the question is, what is the identity of dark matter? And the other big mystery of the universe is that we only see mostly matter in the universe, but the standard model predicts that there should be equal amount of matter and antimatter. So where does the antimatter go? What provides the source of the matter-antimatter asymmetry? So that is the main topics that I want to cover today. And specifically, I want to use the particle called the axion to address all three questions in a very simple construction with various mechanisms. All right, so let me begin with the review of the QCD axion. As we mentioned before, that the neutron has constituent quarks, and just from classical mechanics, you can see that there are some distribution of charges. Unless they're all perfectly aligned, you would expect that there's some electric dipole moment. And you can see the electric dipole moment is basically given by the constituent quark charge and the size of the neutron. But if you want to do a more precise calculation, you have to go to the quantum field theory calculation using this term in the Lagrangian. So this G represents the gluon. And there is a dimensionless parameter theta bar. We don't know what it is in the theory, but we know we expect it to be order one because it's dimensionless and there's no reason for this term to vanish because this term obeys all symmetries of nature. And if you use this term to calculate the electric dipole moment of the neutron, then we find it to be of order 10 to negative 16 times theta bar e centimeter. But the experiments told us that the EDM of the neutron is bounded from above by 10 to the negative 26 e centimeter. That means just by comparing these two terms, you see how the dimensionless parameter has to be less than 10 to the minus 10. And the big question is, why is it exceedingly small when it is expected to be order one? What is making this term vanish? And the solution was proposed by Pache and Quinn in 1977. The basic idea can be understood as follows. You first promote this theta bar from a parameter into a dynamical field. So there could still be some bare contribution from the standard model, just a parameter, but there's an additional field that couples to the gluon, GG dual. And this field is called a QCD axion. Because this is a dimension 5 operator, so you need to have a suppression scale. And that suppression scale is called the decay constant. Eventually, this decay constant is going to be a very large field, large volume, as we will see later. But for now, let's just focus on what happens to this field. If you have this axion coupling to the gluons, then the QCD effects automatically generate a potential for the axion. And the potential looks like this. It is basically a cosine function. And as you can see, to minimize the potential, you want this argument to be small. And by having a small argument, then this is the lowest point of the potential. But the small argument means that theta bar plus A over FA combination should be zero. And if this is zero, that means the overall coefficient of the GG dual operator is zero. So in some sense, it is the potential that drives the coefficient of GG dual to zero. And that is the dynamical solution to the strong CP problem. Because overall, if the coefficient is nearly zero, then the EDM of the neutron is nearly zero. So that's how people have proposed to solve this strong CP problem from the QCD axiom. And now I just want to give you the status of the axion dark matter searches. For illustration, I will use the axion photon coupling. So the y-axis is how strongly the axion couples to the photon. For the purpose of the talk, you can think of it as 10 to the minus 3 divided by FA. But in general, there's some model dependence. The horizontal axis is the axion mass in electron volts. And the fact that we have a Q to the axion, meaning that we have an axion photon coupling, tells us that there's a specific relation between the decay constant Fa and the axion mass. So that is shown by this band. So if we want to solve the strong CP problem, we typically expect the axion to live in this yellow band. And there's some width of the band just due to the model dependence. Here, we just vary the coupling by a factor of 10 to show the model dependence, but we don't necessarily have to live within this band for the QCD axion. And when we have a particle that's outside the QCD band that does not have a gluon coupling, we call those particles ALPS, which is the axion-like particle. So they don't solve the strong CP problem, but they're still very well motivated. All right, so that's the status of the experimental searches. The excluded regions are shown in the shaded regions, and the broken lines here show the future prospects of the proposed and ongoing experiments. Especially the ones that are very deep down here, they're the ones that are searching for axion dark matter. So they assume 100% dark matter. So you would have to have some mechanism to produce dark matter in order to be probed in those deep dashed lines. All right, so now let's talk about how we can produce axion dark matter in the early universe. The idea is that when you solve the equation motion, you're looking at this equation. And this axion, this A is the axion field. Eventually, the size of the axion field value would tell you the abundance of dark matter. And this equation motion is nothing but a damped simple harmonic oscillator. So this term is our familiar friction term. And it is there because of the Hubble expansion of the universe. So this is the Hubble expansion rate of the universe. So that acts as a friction term to this scalar field. To see it more easily, the idea is that we have a cosine potential, and the axion is initially misaligned from the minimum of the potential, unless you fine-tune it or you have some dynamical reason why it is not misaligned. So when we begin with this misalignment, initially, in the early universe, Hubble's rate is very, very large. And that makes the friction term dominate. So the field will be frozen here. But at a later stage, when Hubble drops below the axion mass, then the oscillation of the axion starts. And this is where the CP conserving minimum is. That's where we solve the strong CP problem. So the misalignment mechanism not only explains why the axion needs to go to the minimum of the potential, but it also tells us the axion dark matter abundance, because this potential energy eventually becomes the dark matter energy density. So now you can see how the misalignment mechanism tells you the abundance is basically controlled by the misalignment angle here. All right, so if we want to use that to make a prediction of where in the parameter space we should seed for axion dark matter, then it is predicted to be in this gray band. Here we have to make the assumption that the misalignment angle is of order 1. In this case, this is the region where we explain dark matter abundance from assignment. And if you're above the gray band, then axion dark matter is underproduced because the decay constant is too small, so the number density or the potential energy will be too small. But that brings us a question. Then how do we explain if we do find an axion dark matter particle here from some of the experiments? How do we explain the dark matter abundance of the axion? From the assignment angle, from the assignment mechanism, we will expect it to be underproduced. So this is the big question that I want to answer in this talk today. And this brings us to what we call the axion rotation. So when we talk about the axion as in this Lagrangian term, what you need to see is that it is a dimension 5 operator, which means that it requires a UV completion to the model. And the UV completion always involves the complex field, and it is what we denote as P. So this complex field has the radial mode and the angular mode. The radial mode is basically the scalar field, the real scalar field that spontaneously breaks the Pacheco symmetry in this one bottle potential. When the radial mode gets relaxed to the minimum, that's when we break the Pacheco symmetry spontaneously and generate this decay constant. And axion is the angular degree of freedom. It is the pseudo-Nabu-Goldstone boson of this Pacheco symmetry breaking. And it gets a mass from the QCD effect eventually. But at high temperature, the axion is basically massless. And what we mean by the rotation is what you're seeing in this photo, that the complex field may not sit at the origin or at the minimum of the potential, as the literature has usually assumed. We realize that the complex field can actually get a kick from this wiggle, which I will explain later. And once the complex field gets a kick, then the complex field undergoes this spiral motion. So it's not only relaxing in the radial direction, but it's also rotating in the angular direction. And it turns out that this axion rotation is extremely interesting because not only can it provide the dark matter abundance from a new mechanism, but simultaneously we can explain the origin of the matter-antimatter asymmetry. And what is especially exciting about this paradigm is that we actually did not have to introduce any new ingredients other than the existing axion theories. So we're basically just realizing that this dynamics has just been overlooked in the past decades. We're just taking the standard QCD axion theories, and then we're realizing that it can actually do much more than we thought before. All right, so why do we actually consider rotation? More specifically, what is giving us this kick? So what I'm showing you here is the complex field, and this is the wine bottle potential for the radial mode. And now I want to explain the origin of the wiggles here. The wiggles are there only in the large radius. And why do we have wiggles? First of all, we have to realize that Pacheco symmetry is a U1 global symmetry. And there's a conjecture in quantum gravity that any global symmetry would be broken by gravity. And the way we parameterize it is to have a higher dimension operator. So the operator could be of order this form. And this M is the cutoff scale of the theory. So it could be the Planck scale. And this comes with a higher dimension operator. So this N is a free parameter. And if we live it in terms of N, you can see how this explicit Pigou breaking term is written as cosine. But the coefficient of the cosine is proportional to the absolute value of P to some high power. And this is basically just the radius, which means that when you're at a very small radius, for example, here or at the origin, this term is completely negligible. But when the radius is large, then you see how this cosine term gets enhanced. It becomes more and more relevant. So at the largest radius near the cutoff scale, then the wiggles become very important. And those wiggles are the things that give a mass in the angular direction, or equivalent speaking, it gives us a gradient term or a kick in the complex field if the complex field starts with this large radius. So that's the origin of the wiggle or the kick. And now I want to explain to you why we start with a large radius instead of being at the minimum or at the origin, for example, during inflation. So the idea is that you could have a coupling between this complex field and the inflaton. If you have such a coupling, then the photon can generate the so-called Hubble-induced mass. And this Hubble-induced mass is basically the mass term for the radius. And it can come with a positive sign or negative sign. Let's assume that it is negative. In that case, then the potential during inflation for the radial mode is unstable at the origin, and it gets pushed to a very large field value given by this tachyonic mass term. But this complex field would eventually get stabilized by another higher dimensional operator, and that would make the complex field sit at a very large radius. So during inflation, it gets pushed to a large radius, and after inflation, after the Hubble-induced mass is vanishing, then that's where we start the dynamics. And this higher dimension operator would then give us a kick and generate this rotation in the complex field space. So I should mention that this whole dynamics is analogous to that in Affleck-Dunn barogenesis. One main difference is that we're using the complex field that contains the axion. But Affleck-Dunn is using the complex field that contains the scalar partners of the quarks and leptons. So basically this quarks and leptons. And we just realized that by using that mechanism to initiate the rotation for the complex field for the axion, then a lot of interesting phenomenology follows. All right, so I want to offer you a different way to understand the asymmetry of the Pachequin charge, meaning the rotation. So we want to think of it as a charge now. The reason is that you can think of this Pachequin symmetry as a shift symmetry, and there's always a conserved quantity for any symmetry in the problem. That's the Noether theorem. So you can compute the Noether charge, which is supposed to be a conserved quantity. For this system with the shift symmetry, you find the conserved charge to be s squared times theta dot. S, again, is the radius of the complex field. Theta dot is the angle, a over fa, but the time derivative. So this is the angular velocity in the field space. And this formula is not surprising because this is what we learned in classical mechanics, that if you have a rotational symmetry in the system, the conserved quantity is the angular momentum. And the formula is r squared omega. That's exactly what we get here. Except that now we're using the radius of the field and the angular velocity of the field. So what this is to say is that you can understand this rotation as a type of charge, and we call that charge the Pachequin asymmetry, or the Pachequin charge density. And this quantity is conserved up to expansion. All right, so the next thing we want to discuss is what determines the size of this theta dot. So if you just derive the equation motion, you will find that the equation motion looks like this. This is the potential for the radial mode and the first derivative. And on the right-hand side, it is s times theta dot square. But if you remember from classical mechanics, this is exactly the centrifugal force, because the gradient potential is the force, and the centrifugal acceleration is r omega squared. So it's basically just the balance between the gradient of the potential and how fast it should be rotating to maintain the circular motion. And this theta dot from supersymmetry, it would or the potential from supersymmetry, it would take this form, 1/2 m squared s squared. So it's a nearly quadratic potential for the radial mode. Then using this potential from supersymmetry, we will find that the theta dot is just the mass of the radial mode. And this S in supersymmetry will be called the Axion. And this MS is eventually set by the supersymmetry breaking mechanism, so the Susi scale. So that brings us a very interesting connection between axion physics and the scale of supersymmetry in the model. All right, so I want to talk more about the Pachequin charge evolution. So the idea is that this charge may be evolving over time because of the Hubble expansion of the universe. And R here is the scale factor, and it is being diluted because of the volume is increasing. So now what that tells us is that if you have a quadratic potential, this field square will scale as r to the minus 3. And just from the charge scaling, if s squared goes like r to minus 3, that tells us that the theta dot must be a constant. And this is true when the radius is still very large compared to the vacuum expectation value of Fa. So here, when it is rotating on the body of the one-body potential, then theta dot is constant. And that constant is nothing but what we saw earlier on the slide. That constant should be the Saxon mass. But the rotation is eventually going to shrink in radius, and the rotation will be at the minimum of the one-body potential. When that happens, then this S, the radius, becomes the fixed volume. Then from this scaling above, then you see that theta dot itself has to scale as r to the minus 3. And when you look at the energy density of the rotating field, initially it is scaling as r to the minus 3 because of the S square scaling. And eventually, the energy density will scale as theta dot square, which is r to the minus 6. So what that means is that this energy density of the rotation initially scales as matter and eventually has a very fast redshift. It will just redshift away compared to radiation. So it will transition from matter to kinetion. And there's also a very interesting phenomenology that I would explain further later in the talk. All right, so one more thing I wanted to talk about in the rotation is that the question is, if we have a rotation in the Petriquian sector, if we thermalize the complex field, what will happen to the asymmetry? What will happen to the charge? Do we completely destroy the rotation and put it in the thermal bath, or do we transfer only a small amount? To answer this question, you have to understand that the whole system is in equilibrium, and we want to find the equilibrium state by minimizing the free energy. And this is just using thermodynamics. So the asymmetry in the fermion is given in terms of the chemical potential of the fermion, so mu times T squared. And now we want to see how the free energy of the system changes. For the thermal bath, it is basically just given by the asymmetry of the fermion square divided by temperature square. But for the free energy of the rotation, once you transfer a small amount, it's given by negative theta dot times the amount of asymmetry that you transfer. So when you add this up and minimize it, you will find that the free energy of the total system is minimized when the fermion asymmetry is given by theta dot T squared. In some sense, the chemical potential of the fermion is just given by theta dot. So this is the amount of asymmetry we generate in the bath from the rotation. But you can see how this is much smaller than the initial rotation of the Petriquian charge. And this Petriquian charge is initially given by theta dot times S squared, and this S is the radius. We start from a very large field volume, so this S actually stays larger than the temperature. So what this whole slide is to say is that we do generate some asymmetry in the standard model after we reach thermal equilibrium, but the asymmetry that we generate in the bath is very small compared to the amount of charge that we begin with in the Petriquian sector. What that means is that most of the Petriquian charge remains in the rotation. But this production of the carrier symmetry, it would be important when we talk about the baryon symmetry of the universe. And I just want to quickly go over some subtlety of the rotation dynamics when we put it in thermal equilibrium. So initially, after the cake, the motion is generically elliptical because you get the cake not only in the radial direction by the curvature of potential, but also by in the angular direction. So initially it's elliptical, but once you put it in thermal equilibrium, then the interactions would extract energy out of this rotating field. But we're using PQ conserving interactions. In that case, then we're preserving the charge while we're thermalizing it. So we're basically removing energy without removing the angular momentum. So the lowest energy state will be the perfect circular motion. And then after that, then that is the dynamics that we described. The rotation will continue at large radius and eventually will shrink to small radius. And this is where the scaling of energy density transitions from matter to kinetion eventually. All right, so now I want to talk about the implication for Axion dark matter. The idea is that this rotation will start from a large radius, but eventually, when it gets to the minimum of the potential, it will still be rotating. And this minimum of the one-body potential is where we define the axion to be. So the axion cosine potential is the potential that's along this angular direction at the very bottom. So as you can see now that the complex field rotation eventually would just become the kinetic energy of the axion field. So the basic idea is that now you have a very large kinetic energy of the axion, which can be much larger than the potential barrier of the axion. So the axion could actually be going over the potential barriers in the cosine potential and going around in circle like this. And this is what determines the abundance compared to the misalignment mechanism where it is the potential energy. In this case, it's the kinetic energy. So we call this kinetic misalignment mechanism. So just to illustrate the idea, we have much larger kinetic energy compared to potential energy. So in the conventional misalignment, when the field is about to oscillate because of a decreasing Hubble friction, in our case, this field is still having a very large kinetic energy. So it comes in and it has enough kinetic energy to overcome the potential barriers until the kinetic energy gets redshifted enough and it will get trapped to one of the minima and then oscillation starts there. So now you can see how we're delaying the onset of oscillation and we're also getting a much larger energy than the potential energy provided by the conventional misalignment mechanism. So this kinetic misalignment mechanism has the effect of enhancing the dark matter bond, which implies that we can explain region of Parameter space above the gray band with 100% dark matter. And that gives very strong motivation for the Axion dark matter experiments. They're searching for the Parameter space way up here. So that's one achievement of the Axion rotation. At this stage, we don't have a prediction of where it should be because we can just enhance the dark matter abundance and there's a free parameter in terms of the charge. So we talk about that we have some particularly in symmetry number density, so that's the N. So now let's define the yield to be number density divided by the entropy density. Then eventually the dark matter abundance of the axion is given by the energy density divided by the entropy density. And it is written in terms of the axion mass times the yield of the charge. So that tells us how much rotation we have. And the observed dark matter abundance today is rho over S, which is given to be about 0.44 eV from Planck. Then it tells us that if you want to explain the dark matter abundance from kinetic misalignment, then there's a specific relation between the axion mass and the amount of rotation. So we only know how much charge we need from the cake, but we have no idea how much charge we have. So that's why we don't have strong prediction at this moment. But there's a relation between the rotation and the mass. But the prediction will come in once we talk about the baryon symmetry. And the baryon symmetry mechanism involving the axion rotation is what we call axiogenesis. The idea of the axiogenesis is as follows. We explained before that the axion rotation is understood as the asymmetry or some kind of charge. And the question is, how do we transfer this charge from the axion rotation into the baryon symmetry? And this diagram shows you the flow of the charge. And what is very surprising is that this baryogenesis mechanism is completely automatic because we have standard model processes called the Strong's phaleron and electric Wick's phaleron. The fact that we have a QCD axion tells us that there is a strong anomaly, QCD anomaly, and that would automatically transfer your Pacheco charge into the quark carrier symmetry, which means that you have more quarks than anti-quarks. But at this stage, the baryon number is still zero. It only gets non-zero because of the electroweak phaleron. It would transfer the quark carrier symmetry into a non-zero baryon symmetry. So that is what happens to the QCD axion. But more generically, for axion-like particle, you could have electroweak anomaly so that the Pacheco asymmetry can get transferred to the baryon symmetry directly without going through the standard model quarks. And the final baryon symmetry of this axiogenesis is given by some order one model dependent parameter times the yield, that's the amount of rotation, times the electroweak temperature divided by the decay constant square. And this is the observed abundance of the baryon symmetry. And the reason the electroweak temperature is relevant is because that's when the electroweak phaleron process goes out of equilibrium, so the transfer stops. So we need to know the electroweak temperature in order to predict the baryon symmetry. But the standard model tells us that this T electron weight should be around 130 GeV. So we can use the standard model prediction. And then in that case, then by requiring the correct amount of baryon symmetry, then there's a specific relation between the decay constant and the asymmetry in the Pachequin sector. All right, so now you can see that we may be able to make a prediction now by using both the dark matter production and the baryon symmetry. So this is what we call the Axion or L cogenesis. Cogenesis refers to the idea that we're producing both dark matter and the baryon symmetry using the same dynamics, the axion rotation. So the prediction is done in the following. As we saw earlier, dark matter relates the mass and the rotation, and the baryon symmetry relates the decay constant and the rotation for a fixed electroweak phase transition temperature. Then that means there is a specific relation between the axion mass and the decay constant, and that can be shown in this plot as this. So the green band here is what happens if we produce this the observed amount of dark matter and the baryon symmetry from axion rotation using kinetic misalignment and axiogenesis. So along this green band, both of them are produced correctly, and above this green band, if you require dark matter abundance, then the baryon symmetry is overproduced. And below the green band, if you require the baryon symmetry, then dark matter is overproduced. We call this alkogenesis because this green band lives in this parameter space and it does not touch the QCD axion, so it's axion-like particle, and it doesn't overlap until we're in the excluded region. And again, cogenesis refers to the idea that we're producing both the dark matter and the baryon symmetry of the universe. And this prediction depends on the T electron weak, and we fix it to be 130 GeV. And what is exciting is that there are experiments that are already actively probing our alkogenesis idea. And what is more exciting is that our prediction predicts that the axion photon coupling is stronger than the conventional prediction from QCD axion and the conventional misalignment. So in some sense, before the experiments would be able to probe other benchmarks, they must go through our prediction first. All right, so the final thing I want to touch on is this alkogenesis is the axion-like particle. So can we do better? Can we actually make it consistent with the QCD axion instead? So that would be called the QCD axion cogenesis. And the answer is yes. And the model building is also very straightforward. So the idea is that we want to enhance the baryon symmetry production. And there are many different ways, as long as you have any additional lepton or baryon number violating process in your favorite model. So I will just show you one example, and that's what we call the leptoaxiogenesis. The idea is that we know neutrinos have mass, and the mass could come from this dimension 5 operator. It's called a one-bar operator, and this dimension 5 operator can come from the seesaw mechanism. And this one-bar operator breaks the lepton number, as you can see. So L is the standard model lepton, and H is the standard model Higgs. So this breaks the lepton number, which means that there's additional transfer from here to here, and that enhances the production rate. So I won't bore you with all the details of the transfer diagram, but the basic idea is that it gets transferred into the standard model charges, and then this lepton violating operator generates the lepton asymmetry at high temperature. And this lepton asymmetry gets reprocessed by the electroweak aileron into the baryon symmetry that we observed today. All right, so the basic conclusion about leptoaxiogenesis is that now we're actually able to explain both dark matter and baryon symmetry with the QCD axion. And the prediction is that the axion mass is relatively heavy. So it is sitting around this milli-electron volts or heavier region. And this model is especially exciting because it's explaining dark matter baryon symmetry in the framework of the QCD axion. And here we require the dimension 5 operator to explain the neutrino mass. All right, so just to give you some sense of the parameter space. So there's the radial mode, which is coming from the supersymmetry scale, and this is the decay constant. So the open parameter space is at low decay constant. And for example, you can have the right-handed neutrino mass to be relatively low, for example, 100 or tens of TeV. All right, so I will skip the rest of the talk for the time, and I will just quickly mention that in the beginning of the talk, we have the rotation energy density. We mentioned that initially it scales matter, so you would dominate over the radiation, which is shown in red, so you can come to dominate the energy density of the universe. And we also discussed that when the rotation gets to the minimum of the potential, then it transitions from matter to kinetion, and it will very quickly redshift away. So that means there is some modified expansion rate of the universe, and this has implication for gravitational wave spectrum, dark matter production, and so on. So let me just show you, for example, for the gravitational wave spectrum. This is the standard prediction from primordial gravitational wave from inflation with only radiation-dominated era. But with our cosmology, because of the matter and kinetion domination, we get actually an enhanced gravitational wave spectrum. So this would allow gravitational waves to be more easily detectable. And even more surprising or exciting is that the QCD Axion dark matter makes a very sharp prediction that not only do we know that there's a prediction, but if you get dark matter from kinetic misalignment, we predict that the gravitational wave will get enhanced at exactly this frequency of around 0.01 hertz. So if we can see any of this triangular shaped spectrum, or even the place where it gets enhanced, then there will be a smoking gun of the whole paradigm that we're proposing. And we get similar enhancement from string gravitational waves, but I will not go into the details, and I will skip the rest of the talk. And I would like to emphasize that today I only talk about the implication of axion rotation for dark matter and baryogenesis. But there are a lot more other exciting revenue that we have been pursuing, and also that people have been proposing so far. So this new research avenue is exciting, and I'll leave you with my conclusion slide. Thank you.
Okay, thank you for this nice talk. So if the audience has any question, please unmute yourself and ask.
Well, yes, I have a question. Okay, thanks for your seminar. To your knowledge, are there any model realizations which the mechanism that allows the Axion to reach high values occurs after inflation instead during inflation?
Yeah. So you're asking if we can get this rotation after inflation instead of or are you asking if we get a large field value in the Axion after inflation?
Yes, exactly.
Yeah, you can get large field value after inflation, but the problem would be that if you do it after inflation, then the large field value would take random phase. So some patch of the universe may be on this part of the hill. Some region may be at a minimum, some other region may be at a maximum. In that case, then only certain regions in the universe will get a kick. And in that case, then you don't get really non-zero amount of baryon symmetry, because some other region will get the kick in the opposite direction. So there is production of baryon symmetry and production of baryon and anti-baryon. So in that case, then you would eventually kind of cancel all the contribution.
Okay, that's interesting. Thanks.
Yeah.
Okay,
Thanks.
I have the question, the continuation. So after the inflation, if this thing happen, it's okay, right?
After inflation, what?
I mean, after the inflation, this rotation and misalignment, everything happens, then there is no problem with the generation of the baryon asymmetry.
Exactly. So if we get a large field value during inflation, the inflation would make sure that our observable universe has a uniform phase. So in that case, then the whole universe takes the same phase, gets the same kick in the same direction. And in that case, then there will be no problem with production of baryon symmetry and dark matter.
Okay. Okay, if the audience has any other question, please ask. Okay. Okay, if there is no other question, I have two next questions. So on this plane, mass of the axion and axion to photon coupling plane. So the yellow band is for QCD axions. So other regions are for axion-like particles, right?
That's right.
So initially, why we are not interested to the region like right side bottom, uh, that side like
Uh,
mass is
right
here.
here?
Yes, this side.
Yeah, so in principle, we could be interested in that. But the question is, what is the region that gives us the correct amount of dark matter and baryon symmetry? And just the calculation tells us that the prediction is here. And what happens if you want to move to this region is that if you require the baryon symmetry, then dark matter is overproduced from kinetic misalignment. But if you forget about this whole axion rotation mechanism in general, then there's no reason why we cannot be here. But it just, for example, in this region, even for the conventional misalignment mechanism, you overproduce dark matter.
Okay, okay. And another question is that you said that at one part that when this asymmetry generation probably you said that it will be thermalized. So thermalized
Mhm.
only through for with the photon coupling or with other couplings also.
Good. So any coupling is able to thermalize the complex field. So the only thing we require is that there's some interaction channel between the axion particle or axion field and the standard model. So you can go through the standard model quarks or standard model Higgs, or even the KSVZ quarks, the heavy quarks that can help us get the whole complex field into thermal equilibrium. So axion photon coupling is not required. It's something with barogenesis that we only require some coupling between the axion and the standard model to transfer this asymmetry.
Oh, okay, okay. And the last question, probably another this action field. When you said that after inflation, so
Mhm,
action field was initially somehow was there, right, in the universe, but you are not talking about
mhm.
the origin of the field. So it can okay. I understand if it was there during inflation, it's a problem, but it still can be produced from the inflaton, right?
The axion field.
Yes.
How do you
Like
produce the axion field from the
I mean,
inflaton?
during reheating or something, or preheating, yeah, that time from inflaton some field can be produced. So if I produce the
Uh-huh.
action, there is you have there is no problem, right? The whole universe will get the same asymmetry, baryon asymmetry, and so on, right?
Yeah. Even if you produce the axion from the reheating, the axion would behave as dark radiation because it's ultra light, so it'd be ultra relativistic. But there are two separate components. One is kind of cold axion coming from either misalignment mechanism or kinetic misalignment, and the other component is just relativistic axions. And it is perfectly fine to have both. And in our problem space, the relativistic axions do not generate too much dark radiation.
Oh, okay. So why it will contribute only to the dark radiation, not to the dark matter?
Yeah, because if it is produced from the inflaton, it's too hot, meaning at, for example, at recombination, it is still relativistic. And also the energy density is much too small because axion field is very light. So for dark matter abundance, you need number density n over s, the yield, to be much larger than 1. But thermal production can only give a yield of n over s of order 1.
Oh, okay. So I cannot produce action dark matter from the decay of inflaton.
No, yeah,
Okay.
that would be inefficient, insufficient, and also too hot.
Okay. Okay. Thank you. So, if the audience has any other questions, please ask. Okay. If there is no other questions, let us thank the speaker for this interesting and nice talk. Thank you.